Okay, I wanted to address a couple questions that came up today. This was find the sum of this one, and it's not geometric, so I want to kind of address how to do this. Well, it's really actually pretty easy as you realize it's odd powers, and if this were x, what would that be? It would be the sine of x, but where are we evaluating it at? We're evaluating it at pi. Okay, what is the sine of pi? It's simply 0. So the sum of that series, although it is not obvious, is just going to be 0. Okay, so our next one I want to do was one, this is on page 530, it was the sum of the telescopic series. The other ones I want to do are the conditionally convergent ones, 43 and 45. Okay, in order to make this one a telescopic series, we have to make it look like one. So we have to do one of our fun little tricks, which we have to do it and break it down into two fractions. So we got to do partial fractions. So if I multiply this out, I would get 2 is equal to a times n plus 2 plus b times n plus 1. And by the way, if you look at the denominators, they're only 1 unit apart, so that means there's only going to be one uncovered term once I find a and b. Okay, so my convenient values I'm going to pick are -2, and when n is -1. So when n is -2, I get 2 is equal to -b. So b is -2. And when n is -1, I get 2 is equal to a. So what is our series? It's 2 over n plus 1 minus 2 over n plus 2. Because remember, why do I do this? If I do it for a integral, I do it for a series, because we've essentially said that a series is an approximation for an integral, and vice versa. Okay, so let's go map out terms. This starts at n is 1, so when n is 1, I get 2 over 2, which is 1 minus 2/3. When I plug, so let me plug in 2 here. So I get 2/3. Plug in 3 here, I'm going to get what? 3/4. I'm going to do one more, and I get, 2/4, and then I get 2/5. Now if I plug in 1 here, I get, or 2 there, I get 2/4, and then I'd be subtracting 3/5, or 2/5. Wow, I can't get those right. Then I'd be subtracting 2/6. Well, if you look at this, these terms are gone, so what is left is 1. So what's our sum equal to? 1. Okay, if these were 2 units apart, then you'd have 2 uncovered terms. You'd find the sum of those two. Okay? All right, so the next one I want to go do is number 43, conditionally or absolutely convergent. Well, this is either absolutely convergent, or it's divergent. The only time it can be conditionally convergent is if it's alternating, and this one's not alternating. Okay? So this one takes a little bit of a jump to make sure we understand. Is we need to do a little comparison here, and the natural log of n relative to n is always less than it. Value for value, because if I look at this, if this is 1, this is the natural log of 1. It's always less than. If this is 2, 2 is bigger than the natural log of 2. 3 is bigger than the natural log of 3. Okay? So if I understand the natural log of n is less than n, well, I'm going to divide them by the same thing, which is n cubed. Okay? So we're pretty sure, or we can absolutely say, that since we divided by the same thing, that this series is less than this one. Well, and if I simplify that, isn't that 1 over n squared? Okay, because we're really doing what's known as a direct comparison test. Okay? Which we'll actually use on 45 also. All right? This reduces to n squared, which is a convergent p-series. Okay? Anything that is smaller than a convergent p-series will converge, but anything bigger than it, I can't draw any conclusion on. Okay? Since this one is smaller term by term, this is also going to be smaller. And if a series, for at some point, term by term is smaller than a convergent one, it will also converge. Okay? So this really converges by the direct comparison test, okay, and because this is not alternating, and it's really the same thing as if you take the absolute value of it, you get the same thing. It converges absolutely. Okay? Now, converge conditionally means is the alternating one converges. This one does converge, we converge by AST. If I take the absolute value of it, I get 1 over n. This diverges. Because if the absolute value version of it, which is this converges, then we say it's absolutely convergent. Okay? If this one diverges and this one converges, we say it's conditionally. What condition is it must be alternating? Okay? But the answer of 43 is it converges absolutely. Okay. The last I want to do is number 45, which is this one. All right. So we first want to go check and see. I mean, you can check one or both, but if I just do this one first of all, but well, actually what you should do is check the absolute value version of it, because if it converges absolutely. Okay, so it doesn't matter. So let's go ahead and just test this one as I keep changing my mind on this. Okay, so first of all, your key is it's alternating. So it's alternating. Okay, is a sub n plus 1 less or equal to a sub n for 1 over natural log of n plus 1? Well, as n gets bigger, okay, this gets smaller, so that works. And the limit as n approaches infinity of 1 over the natural log of n plus 1 does in fact equal 0. So this one converges by AST, which by the way, because we know that, it doesn't diverge. So that one's now out. Okay? So now let's go do the absolute value version of it, which is just 1 over the natural log of n plus 1. Okay. And to correct myself, I had emailed Nathan, and he had told me, or he had asked me about this. I said that you can integrate. You cannot integrate it. Okay, so we do need to do a direct comparison on this, but I'm not going to do the 1 over version. Is I'm going to just look at, based on what we did before, is I'm going to compare it to n. And if I plug in n as 1, I get the natural log of 2 versus 1. Well, the natural log of e is 1, and this is smaller than it. So again, this is smaller. When n is 2, I get the natural log of 3. Well, this is bigger than e just a little bit. Okay, so it continues to be bigger. So the natural log of n plus 1 is less than n. All right? So now we have to make a comparison of, well, what happens if I take its reciprocal? Well, what happens now if it's 1 over each of those? Well, if this is smaller than this one, its reciprocal will be what? Will actually be bigger, term by term. Okay? So now I have to look at this one that I'm comparing to. Is this it's a divergent p-series, because p is 1. And this one is bigger than a divergent. So what must this do? Is it diverges by what? Direct comparison. Okay. Now, where is direct comparison the most commonly used? Is for natural log. And what do you compare it to? N. Okay. Because you can make this comparison. This is an easy one to see. Okay. And then once you got to make the jump to reciprocal. Well, if a number is bigger, its reciprocal must be smaller. Okay. So that is by direct comparison. So what is our final answer here? Well, the absolute value one diverges. It diverges, and this one converges. So we say it is. This problem is conditionally convergent. And you might maybe say, what do you mean by conditionally? The condition it must have is it must be alternating it must be alternating to converge. The absolute value of it doesn't. If that one would, we'd say, if they both would, then we'd say it would be absolutely convergent. Okay? Hope this helps. Have a good one. Bye-bye. If you need help, by the way, on error, remember there is something on the error on my website. If you go to the Chapter 10, there's an error, there's a Taylor and error tab that I showed you guys in class yesterday. So, all right. Have a good day. Thank you.